Laminate texture works, metallurgy behind real wood illusion.
When you run your hand across a premium engineered wood surface today, you are interacting with what the industry calls Embossed-in-Register, or EIR. It is a deliberate physiological illusion. The haptic feedback, the physical ridges and valleys your fingers feel, perfectly matches the visual grain printed underneath, tricking the brain into perceiving a raw, natural material. Yet the process required to synthesize that organic feel relies on some of the most extreme, inorganic industrial forces imaginable. Scaling this product globally requires a dual-track mastery of the physical and the chemical, sub-micron metallurgical precision to create the haptic illusion, and isotopic carbon testing to verify the material's biological origin. To understand how these two worlds converge, we have to reverse engineer the modern laminate board, starting from that finished surface and digging all the way down to the atomic level. In modern manufacturing, a truly natural feel is actually the result of the most rigid, mathematically precise tooling in existence. The critical bridge between digital texture design and a physical board is the steel press plate. This is Moldart, India. They manufacture the specialized stainless steel press plates required for modern laminates. In the lamination value chain, a single press plate represents a massive single point of failure. If the metallurgy of the plate is flawed, the entire physical illusion shatters. The path to organic realism has to begin with specialized industrial steel. The first step in creating that illusion is transferring a 3D texture from a digital file into the physical press plate. Historically, this was done using chemical etching. Today, the industry standard has shifted to pulsed fiber laser ablation. This side-by-side performance chart shows the efficiency gains of pulsed fiber laser ablation. It operates twice as fast as traditional chemical etching, while completely eliminating the need for chemical etchants. Stripping out the unpredictable variables of a chemical bath is what enables the millimeter-by-millimeter synchronization required for EIR. A 3D camera physically probes the surface of the tooling to ensure the physical trough carved by the laser maintains absolute alignment with the digital print. Replacing chemical unpredictability with digital laser precision is what makes highly customized lot size 1 production runs possible. Once the microtexture is mapped, the plate itself has to endure the extreme scale and pressure of the lamination press. This schematic isolates the press plate's core layer, martensitic chromium stainless steel, Avesta 393 HCR. For high-impact pressing, surface hardness stays between 40 and 50 Rockwell, with roughness capped under 0.25 micrometers. At 400 degrees Celsius, its low thermal expansion coefficient is a critical metric. If the plate stretches unpredictably under that heat, the physical texture will misalign with the board's printed grain, destroying the synchronized illusion. Which brings us to the final, most demanding geometric tolerances shown here: parallelism and thickness. The tooling maintains parallelism to 0.03 of a millimeter across the sheet to guarantee uniform pressure. The aesthetic beauty of high-end decor is entirely dependent on the mathematical rigidity of this martensitic chromium steel. Below the press plate sits the substrate itself, the physical board receiving the texture and the print. Modern substrate manufacturing is moving away from traditional melamine-impregnated paper in favor of direct-to-substrate digital printing. Printing directly from a digital file eliminates plate setup costs entirely, making it economically viable to produce a single, unique unit on demand. Structurally, the composition of the board is bound by strict ANSI and AWI standards to ensure visual uniformity and prevent defects like chip-out. But the ultimate barrier to entry for a premium board today is passing the sustainability truth test. This diagram illustrates the ASTM D6866 standard. It utilizes a rigorous isotopic analysis to contrast a bio-based carbon-14 atom against a petroleum-based carbon atom. By utilizing radiocarbon analysis, laboratories can scientifically prove the exact percentage of living biomass contained inside the board. Achieving certified bio-based content, scaling from 20% to over 85%, is now a non-negotiable requirement for green building certifications like LEED v5. A premium board must simultaneously act as a high-definition digital canvas and a verified biological asset. Stepping back from the individual board and press plate reveals the larger manufacturing floor and the strategic outlook for the rest of the decade. Driven by a shift toward fully automatic CNC systems, the woodworking machinery sector is experiencing a 3.9% compound annual growth rate, projected to reach $66.3 billion by 2033. At the center of this growth is the concept of the digital twin, visualized here as a glowing wireframe mirroring a massive physical CNC press. This dual-layer synchronization is projected to be an industry standard by 2026. The digital twin actively predicts tool wear on those hardened steel plates and autonomously optimizes feed and speed rates to prevent failure before it happens. Overlying this network is the integration of agentic AI. This system provides autonomous reasoning capabilities, optimizing global supply chains and capturing institutional manufacturing knowledge that would otherwise be lost to turnover. Predictive, autonomous digital ecosystems have largely superseded human intuition in the management of physical metallurgy. This complex technological stack ultimately converges directly at the consumer level in the form of what the industry calls smart surfaces. The modern board is now capable of embedding IoT sensors for occupancy, temperature, and wireless charging directly into the substrate itself. Because of these embedded integrations, the smart furniture market is projected to hit $9.12 billion by 2031. The future of woodworking is a highly integrated technological stack. The organic feel of tomorrow's architecture relies on absolute isotopic verification, autonomous digital oversight, and millimeter-perfect steel.